Hi everyone, so in this video we discuss various methods for handling depth in recurrent neural networks. So basically you can, as shown on the left here, you can of course have a stack or a chain of recurrent networks. Each has a hidden-to-hidden connection as we had before, and thereby you can have a deep network like that. But more interestingly, depth can be also input or fed, can be part of the recurrent connection itself. So for example, here, like we have a hidden-to-hidden recurrence with maybe one layer in the middle or even more layers in the middle, and then you have the recurrence relationship. So when you unfold the computational graph, the connection between h of t and h of t plus 1, you could basically insert another network in that connection, not necessarily only one layer as we had before, or not necessarily a direct fully connected connection. And moreover, these connections, the hidden-to-hidden recurrence, do not have to be fully connected. So the W matrix could be sparse or convolutional, maybe. Right? So all these options are there, but let's discuss the implications. So basically, when you add depth in the recurrent connection, you are allowing for more interesting phenomena to be captured in terms of the temporal correlations, right? But optimization, so the cost of that is that, so the advantage is similar to the advantage of why you would have a deep neural network in the first place, right? So with deep learning, you could have impressive generalization performance given that you engineer the network or the layers in between the recurrence relationships between the successive time steps correctly, right? But the problem is that, so far we mentioned that this W that you have from h of t to h of t plus 1 could be very sensitive, right? Because both in forward propagation as well as in back propagation, this W gets exponentiated by a number that is proportional to the sequence length, right? So any change in that W from the ideal one could have an error that is also being exponentiated to a large power. So if you have a deep network, right, in place of the W or in place of the one layer, right, and this is the W I'm talking about, the H to H, right? So if I have a deep network, it becomes even harder to guarantee that there will be no imperfections in the learning process. So it becomes very difficult to optimize, right? So that's why, like a common thing that you will see in deep recurrent networks where depth is part of the recurrence relationship, that there will be a skip connection that gives basically direct access, right? So a parallel skip connection, as in the picture here, right? As in this example, where that skip connection allows for mitigating the problems related to the vanishing and exploding gradient, right? By minimizing the shortest path between h of t and h of t plus 1. So that if the deep path or if the longer path has an error, the shorter path can basically compensate for that, or make you enable the network to neglect the longer path if it's erroneous, right? Now that depth can be added in the input to hidden connection, in the hidden to hidden recurrence, or in the hidden to output connection, right? So you could imagine all combinations where the depth need not to be in the hidden to hidden recurrence. Maybe the X to H is a deep network, maybe the H to O or the output is a deep network. Sounds good. Now another alternative is what's called recursive neural networks. And basically recursive neural networks are doing the following. Instead, so in the usual network, right, this X, and then I have H, and then H connected to itself, right, and then O, right? So if I unfold the computational graph corresponding to that network right here, right, then I will get a chain in time. What recursive networks do is that basically the alternative is, instead of a chain in time, you can have an arbitrary structure in time. And that, so here x of 1 corresponds to x at the first time step, x of 2, x in the second time step, 3, third time step, and so on, right? So here I am processing the inputs at different time steps differently, right? So I have an arbitrary tree-like network, right, that has a structure that tells me that I should process the different time steps in a different way. That could of course alleviate a lot of the problems related to exponentiating the same way parameter, because here these connections, right, could be different. So I could have W1 here, W2 here, right, W3 here, and so on, right? And by having different weight parameters, that alleviates a lot of the problems related to the depth, right? Because like if I have the same number, I'm exponentiating it to a large power. If that number is slightly above 1, then I will explode. If that number is slightly below 1, then I'll vanish, right? But if they are independent numbers, that's unlikely to happen. So what's likely to happen is that they will compensate for each other, right? The errors in them will be independent. And another important thing is that it basically the tree-like structure will significantly reduce the depth. So instead of a depth that's equal to the sequence length, as in the case on the left here, right, where you have a chain in time, here typically for a tree you would have order logarithm of the sequence length, right? So that can be very helpful. So the recursive neural networks are basically can introduce a lot of optimization advantages for training the recurrent neural network. But of course it becomes very difficult to optimize, because you have to choose the right choice of the structure of the network has to make sense, right? Another advantage is that they allow for time sensitive information to be captured. Then we can go back here to this, remember that example where you are processing, let's say, sentences. And depending on the position in the sentence, you should have you should learn different parameters. The same thing about the example where we talked about the movie scenes that are processed by a network that's trying to extract a trailer for the movie. So it depends whether the scene is at the start of the movie or at the end or in the middle of the movie, right? So if you are curious in knowing more about these recursive neural networks, I encourage you to read this paper called From Machine Learning to Machine Reasoning. And also you can read a lot of literature about specific applications. For example, natural language processing, where the parsing tree of the sentence is used as an architecture for the recursive neural network. And that approach is followed in this paper here, Recursive Deep Models for Semantic Compositionality over a Sentiment Tree Bank. And last but not least, there is interesting literature on basically learning the tree structure, or learning the architecture of the recursive neural net, learning how to process the different points in time, the inputs at different points in time differently. So in general, depth in recurrent networks is an open research problem that's very interesting, because it has a lot of aspects that could have a dramatic impact on the output, like the skip connections, whether skip connections through the depth, right, or skip connections through time, which we'll discuss in the video after next. And so there is a lot of optimization implications on these choices, and also statistical implications on capturing the longer term temporal correlations. Thank you.